everyone. Welcome to the Trial Site News interview series. I'm Dr. Erin, your host. And today I'm excited to have two scientists and researchers with us. We have Dr. Jorge Almodovar and Dr. Raj Rao, and they are going to talk about research that they're doing in the area of stem cell engineering, biomedical engineering, neat stuff. So thank you guys for joining us on Trials. Yeah, absolutely. And where are you guys based?
So we're at Arkansas, the University of Arkansas in Fayetteville.
University of Arkansas. Okay, that's where you both are. So maybe let's start out. Do you guys mind giving an introduction about who you are and the type of work you do? Sure. And whoever wants to go first, jump in.
Yeah, I'll take I'll go first. So I'm an assistant professor of chemical engineering at the University of Arkansas. So all my training, or my degrees, I guess I should say, have been in chemical engineering, but really my research has been mostly in biomedical, in the field of biomedical engineering, and particularly in the area of biomaterials. And so really what my lab is focusing on is on developing biomaterials for multiple application in healthcare, spanning from tissue regeneration to stem cell therapies, cell manufacturing, and pretty much a little bit of all. And primarily, we are developing these biomaterials using natural-based polymers such as collagen and stuff like that.
Very interesting. Thank you. Dr. Rao?
Yes, again, thank you, Erin, for hosting us. So my area of research over the past 20 years now has been the area of stem cell engineering, focused on engineering microenvironments for better exploring the properties of stem cells and derivatives. So broadly speaking, we work with different flavors of stem cells, with different potencies, so to say. And the idea is, figuring out ways to either grow more of them or to differentiate them into specialized cell types for ultimate applications in the field of regenerative medicine and cell-based therapies. So working with Jorge, we're really exploring certain properties of human mesenchymal stem cells and how better to grow more of them, so that we can have more to work with under very specialized conditions and differentiate them into specific cell types for applications in cell-based therapies to treat different diseases.
Okay, thank you so much. So you guys just received a pretty large grant from the National Science Foundation, specifically to investigate how engineered coatings imitate the surrounding cell matrix, influencing human mesenchymal stromal cells, or something like that. And you can correct me if I botched that in any way, but that's a lot for someone to understand, and even myself. So I was wondering, can we start with the basics? Can one of you guys jump in and explain what are these mesenchymal stromal cells and why do we care about them?
So I'll go ahead and talk about the cells specifically. So the specific cell types we are working with are human mesenchymal stem cells, or they're also classified as human mesenchymal stromal cells. And these cell types are found in different tissues of the human body. Most prominently, they are found in the bone marrow, and they surround other specific stem cell types called the hematopoietic stem cells. And so they play a very important support role in enhancing properties of hematopoietic stem cells. But equally important is the fact that these human mesenchymal stem cells have their own unique multipotent potential to differentiate into very specialized cell types like bone, cartilage, tendon, ligament, fat as well. So as I mentioned before, these cell types are also found in other tissue types. So another exciting opportunity is deriving these specialized cells from fat tissue. And again, ultimately, the goal is to use these cells in stem cell engineering paradigms to differentiate them into specialized cell types. So the bottom line is that these cells are present in each one of us, and we have the opportunity to extract these cells from our own bodies and and create some unique microenvironments. And Jorge will talk a bit more about some of the matrices that he's developing in his lab to enhance properties of these cells.
Perfect. And that's a perfect lead-in to my next question. This matrix, this surrounding matrix of these types of cells, why is that important? Why do we care about that? How do the two of those interact?
Sure. So basically, if we look at our different tissues, at really any tissue or organ, if you look, down on them, they're mainly composed of cells, right? And the environment that's surrounding them, right? And that environment can be very complex and it is very tissue dependent. But in general, it's composed of many proteins and natural polymers, such as polysaccharides, such as glycosaminoglycan, and this, you can imagine that it's sort of like a surrounding mesh or a net that is covering all the cells, and it provides a bunch of different signals to the cells that ultimately control cellular processes in both healthy cells and healthy tissues, and even in disease or damaged tissues as well. The extracellular matrix plays a critical role in tissue regeneration as well, by providing all sorts of different biochemical factors that guide cells as well, sort of trap those factors and present them at the required concentrations and at the required timing. The extracellular matrix also provides not only mechanical support, but mechanical cues as well, right? And so, it varies very differently from tissue to tissue, from like hard tissues like bone to soft tissues like nerves and whatnot. And so what we are trying to do is mimic that native microenvironment. Now it's like I've mentioned, it's a very, very complex microenvironment. So we're really, we're not gonna fully recreate it, but at least we can make part of it and provide some of those cues in the hopes that it would ultimately make the cell essentially better. So if you can imagine, cells in labs and even at larger scale in the industry, they're cultured in these really hard surfaces that are, and keep in mind, these are cells that need a surface to attach, this MSCs, the cells that we're working with. So they're usually cultured in really hard surfaces that are created using synthetic polymers. So really, really far removed from their native environment. And many studies have shown that those culture conditions can actually lead to, well, for the cell to have a less therapeutic capacity when we're talking about using the cells as a therapy. And so, our idea is that if we can recreate part of that environment and provide something a little bit more closer to the cells, but at the same time using a method that can be adaptable to what the industry currently uses to grow these cells, right? We're not, we're realistic. This type of reactors are going to continue to be in use. So if we can find a simple method that we can adapt to different platforms, then perhaps that would create a better cell product. And basically that's, the heart of this proposal.
The gist of it. So I'm thinking along the lines of, I like metaphors. So I'm thinking like an ecosystem to keep, right? So that the cell, we all have our own little ecosystems, our communities. It's kind of, and they obviously that influences if we're healthy or not. So I'm sort of picturing a similar thing.
Yeah.
So when you guys talk about engineering coats, what exactly does that entail? What are these coats made of?
Yeah, no, that's a great point. And going back to this idea of recreating their native environment, one of the main components in that environment is collagen. And that is true for all tissues. There's different type of collagen, but collagen is a key player there. And then another very important polymer that is involved in the extracellular matrix of many tissues is this sulfated glycosaminoglycan known as heparin. And so what we've done is that these two polymers or these two molecules behave as polymers as well, and so we can exploit that to create coatings. And what's even nice about this polymer is that both of them have electrostatic charge, a positive or negative charge of the overall molecule. And so what we do is that we'd exploit those charge, collagen being mostly a positive charge at the conditions that we work with, and heparin being mostly a negative charge. So we exploit those interactions to create coatings. And literally what we do is that we expose the surface to a solution of the polymer. It will absorb through electrostatic interaction, rinse it a little bit, and then expose it to the other solution of the polymer, which will absorb through the electrostatic interactions. And we keep doing that, creating a very thin coating. These are nanometer in scale, which is good because it doesn't change the bulk properties of the material that we're using at that level. But in spite of being such a thin coating, they're enough to cause significant differences to the cells and how the cell responds to the environment. And we believe that it's because we're providing not only those biochemical signals from the polymer, but also changing the mechanical properties that the cells are sensing. So now, if you can imagine, it's like you have a hardwood floor, right? And then all of a sudden you lay a blanket, so it's a little bit softer, right? The floor is still there, it's still really hard, but you feel a little bit of the softness of the blanket. So it's sort of the same idea, right? So the cell is sensing that softness that's a little bit more similar to what it is in their native environments and their native tissues. And so that's what we're trying to do. And this process of the coatings is constructed through this technique known as the layer by layer assembly. And what's nice about this technique is that we can apply it to pretty much anything. So anything, it's like paint. You can paint pretty much any surface, right? So it's the same idea with this coating.
Interesting. I like all of the imagery you use there. So now this grant for this future research that you plan on doing is based off of positive results, if I understand that correctly, on some research that you've already conducted. I was wondering if you guys could talk a little bit about that.
Yeah, I mean, this is some work that has started several years ago, where we're looking at sort of the same idea, right? We were looking at different type of coatings and see if they improve cellular behavior. We ran across this specific pair, and we saw some very interesting results. And what that led us for this particular grant is that we're using this grant to sort of understand why we're observing that. And so we're focusing more on mechanics like the cell mechanisms that or the cell signaling pathways are being activated by our surfaces, and sort of have a deep understanding on why the cells are behaving the way they're behaving, with the idea that if we can understand them well, then we can engineer our surfaces to be even better.
Okay, so do you have specific research questions already written out, so to speak, for like a protocol?
For this particular proposal or grant?
The future, or just trying to get a little more specific understanding of like the broad thing you're trying to figure out is why the cells are, or go ahead, Raj.
I think that's a very important. So just adding on to some things that Jorge mentioned. So ultimately what we're trying to focus on is what's happening to the cell in the context of having these specific engineered matrices in place. So because we know that the cells respond to the microenvironment, as Jorge mentioned earlier, they respond to the mechanics of the microenvironment. They respond to the components of the microenvironment. So we really focused on, again, using a bio-inspired approach, trying to mimic as much as possible the components of the microenvironment for these particular stem cells, and create that using these unique technologies that Jorge has developed in his lab, and then see what's happening to the cells. So what we are trying to see is that what signals come out from this microenvironment that the cells respond to. And the way we're going to look at the outcomes we're going to check on are the cells able to proliferate? Are we able to make more of these cells? Are the properties of these cells maintained? Do they continue to express specific markers? Do they continue to express the ability to differentiate into specialized cell types that they would typically do in their native environment? So because ultimately we are trying to create the microenvironment, but in a very simplified form. And so have very unique components of microenvironment that could do most of the job that the cells can do. So I think ultimately that's sort of the broader question we are asking in the context of the research. So really going to see what's going to happen to the cells, what are the signaling pathways that might be activated in the context of this particular microenvironment that will promote proliferation, that will promote growth, that will promote differentiation into specialized cell types.
Great, thank you both. So last question here, from a practical standpoint, and for people who may not know much about cells and biomedical engineering, what sorts of diseases or pathologies could answering some of these research questions potentially help out with?
Yeah, no, that's a great question. And that's sort of what's fascinating about these cells is that they can literally be used for almost any type of disease out there. I mean, I've seen some clinical trials out there where they use MSCs for a number of diseases, immune-related disease, such as graft versus host disease, cancer, anywhere from kidney disease, a lot of COVID-related disease as well, like lung disease, or respiratory disease as well. You name it. Pretty much any type of disease out there, these cells could have the potential to be used for. The challenge here is that for many of this disease and even the clinical trials out there, they have shown some promising data, but they require a huge number of cells per patient per dose. And that's sort of the engineering challenge here. These cells, they can grow fairly well outside in reactors and whatnot, but we need in the order of, millions of cells per dose per patient, right? So, you can imagine that that's a really grand scale challenge. And so what we're tackling that challenge by saying, if our surface can increase the cell growth and that rate of ultimately obtain more cells, then that could potentially lead to not only perhaps better, more therapeutically relevant cells, but even perhaps lower the cost of manufacturing these cells, which ultimately would translate to lower cost to the patient, and make this type of therapy a little bit more accessible to the patients. So yeah, that's ultimately what I think we're trying to do. So.
Fascinating. So
one thing I'll add on to what Jorge mentioned, specifically in the context of cellular biomanufacturing. So one thing to realize is that there are a lot of existing systems in industry specifically that have been developed for growing cells. But the important thing to note is that most of these systems that have been developed for growing cells are really not focused on using the cells themselves as products. They are focused on using these cells to generate specific therapeutic proteins or antibodies, etc. So there has to be a slight paradigm shift when we think about biomanufacturing for cells, because the cells themselves are the products. Mm-hmm. And so that's where we really need to focus on creating these unique microenvironments that will allow us to, better enhance the properties of these cells before they can be used in regenerative biomedical therapies.
Okay, so just to summarize that for people, the problem is getting these cells to scale. You need a bunch of them. So you have to figure out how to make the best cell first, and then you have to figure out how to scale that. So, wow. Okay. So there's a lot of research to be done. I'm glad you guys are in the research game here. Fascinating stuff. Anyways, any closing remarks? Anything that you feel you want to?
No, I mean, I guess not really. I just wanted to thank you for giving us the time.
Absolutely. Thank you both, Dr. Raj, Dr. Jorge, for coming on. Thank you for our listeners at Trial Site News. I hope you guys enjoyed this episode. Leave a comment, tune in, subscribe. And if you guys ever want to come back on and you finish, if you get some research results, definitely let us know. I'd be happy to have you back on again. I think this is really interesting stuff.
Thank you. Thank you very much.
Thank you, Dr. Aaron.
Absolutely. Enjoy the rest of your day, guys.
Bye.
Bye-bye.